Hi everyone. Today's notes are going to be on Algebra 2 and Algebra 2 Honors, Domain, Range, and Notation. And I'm combining today's notes simply because the only difference between the Honors and the on-level class is we take out one little kind of notation language in the Algebra 2 level, where in Algebra 2 Honors you just get one little extra tidbit, but it's mostly focused on something that you may or may not use in higher level calculus and analysis. Algebra 2 kids, feel free to just watch along if that's something that interests you. If not, you're honestly not missing much. Mathematicians, we have a tendency to love making up new definitions and ways of saying the exact same things. I think it makes us feel smarter. That being said, we're starting with today's notes are on domain, range, and notation. Okay, so the first thing that we should talk about is what is domain? What is range? Hopefully in class I've already covered why these two things are so useful, especially when we look all the way to the right of a graph or all the way to the left of the graph. But if we are being concise, domain, we are talking about the all of the x values, the entire set of x values that make a function true. So all x values, oof, cannot spell. It's okay, I'm a math teacher. All x values that are true in a function. Or maybe not even a function, just all x values that are true on a specific kind of graph that we're looking at. It may or may not be a function. So yeah, we're looking at the x values, so that means we're looking at all the possible values that could happen on the x-axis. So let's say I had a graph like this. Right? So this is our x-axis and this is our y-axis. Then that means if I have, I don't know, let's say this is some function I'm looking at. Doesn't matter what it is. Then if I'm looking at the domain of the function or the x values of the function, let's use a good color for this. So if I'm looking at the domain in green, then I'm looking at the x values, and that simply means I'm taking a look at where this graph, this line, this function or curve is possible along the x values of the axis. So if I look at a point here, then, oh yeah, there's definitely an x value that's possible there. It lines up. If I look at a value here, then I know there is an x value somewhere here that lines up and makes that true. Since these arrows keep going in both directions, then and they keep going and going, and we have no idea when they stop. That's what the arrows mean. Then we know that there's a very real possibility that all the x values, all possible x values, are true on this function. So many times, especially when we're looking at continuous functions, and I'll talk more about what a continuous function is in a bit, but many times we say we're talking about all all real numbers, and we see that symbol quite often, all real numbers. So in this particular example I'm looking at, then the x values, they just cover everything. They cover every single real number that's possible on the x-axis. So if the x values or the domain is considering left and right possibilities, then let's say I choose red for my range. Then if I look at range, then I must be talking about all possible y values that, let's see, how did I say it, that are true in the function. So in this case, my range or the y values, oops, my range, is talking about if I went somewhere over here, maybe, and I tried to find a point and said, well, is there a y value there that is true? Does that actually happen? And if I go over here, all the way to my y-axis, then yes, indeed, it looks like this line hits this part of the possible y values, and the same could be said for down here. This y value all the way down is possible. It is true on this function. In fact, since it keeps going up and it keeps going down, then it's the same for range. We'll say that this range covers all real numbers. And one more time so that we can really see it. If I wanted to, the shorthand notation that all mathematicians use for real numbers is two lines, two big strong lines, and then you draw an R through it. This is the mathematical symbol we use to represent the set of all real numbers. And we're going to see this very often, especially with, like I said, continuous functions, with this, which this one is. Okay, so we've covered the basics of what's domain, what's range. I think to really get a feel for the notation that we're going to use, because currently all I've used is how do I describe the domain, how do I describe the range of this random function in words. And in those words, I've said it covers all real numbers. That's all I have to say. And there's a couple of other ways that we could describe it. And like I said, for Algebra 2 and Algebra 2 Honors, the only difference is the Honors class, we just cover one more kind of notation. But before we get there, let's talk about continuous. I think that's how you spell it. Continuous and discrete. Okay, so these are two opposite sides of possibilities of what a graph could look like. So if I have a function like the one I wrote up here, where I just drew a line all the way, and not once did I take my pen off the page. So let's say I had something that's very familiar. Let's say something that looks vaguely like y equals x squared, a parabolic function or a quadratic function, then without leaving the page, this function is continuous. It flows all the way through every single point that it hits. So if this is continuous, then that must mean if I took a look at a function that could even hit the exact same point. So let's say it hits the major points that we can find on y equals x squared, like 0 or 2, 4, and it looks a whole lot. Not gonna sneeze. Looks a whole lot like our quadratic function. But what's the difference here? Because I just drew a discrete function. What's the difference? Hopefully it's easy to notice that one of these, like I said, is this flowing line. Never stops, keeps going through every single point it touches, every little minuscule point. It's not just hitting x equals 1. It's hitting x equals 1.00001, and then x equals 1.0000001, and so on and so forth. Every possible infinitely many points in between, it's flowing and continuous through there. Whereas in discrete, it's dot, 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 point. I have a point here, a point here, a point here, a point here. And what that is telling me is that there is space between this point and this point. There is space. And Honestly, it doesn't matter how much space is in between those two things. It could be as small as a millionth of a digit, and as large as this point starts at x equals 1, and then the next point we possibly see is at x equals 1,000. It doesn't matter how much space is in between. The point is that there is space in between. It's not flowing, it's disconnected. So this is discrete. Um, when we're looking at functions that are either continuous or discrete, it's important that we are able to call these out. It's pretty easy, mostly because if the function never stops, if the line keeps going and flows, it's continuous. If there's gaps in between where points hit, or if it's just single points on the graph. In fact, it doesn't even have to look like a quadratic function. It doesn't even have to look like something that is a function. I could draw a discrete graph that had a point here, a point here, a point here, a point here, a point here. Oops, a point here, a point here. This whole thing is discrete. It's a discrete set of coordinates, and that's some of the functions or non-functions that we're going to be looking at. So, continuous and discrete. Can we tell the two apart? I think it's pretty straightforward. So the first set of notations I want to cover are going to be continuous, because these are a little more tenuous. Yes, continuous. These are a little more intuitive of how we should write these down. The discrete ones, the ones where like you have point, 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 they're a little less straightforward on how we should write them down, but not too complicated. But we'll do one at a time. First, notations for continuous. And the notations, the possible kinds of notations, are the same for both. So we already covered the first kind of notation. And that's, can you describe what is the domain, what is the range in words? Can you describe it in words? And in continuous functions, almost always when we describe continuous functions in words, we're going to include somewhere in that description that the domain, let's say we're talking about the domain, has x being an element or a part of all real numbers. Or the domain is all real numbers. These are two ways of saying the same thing. Or the range is all real numbers. Y is an element of big R. So continuous. When you think continuous, think all real numbers. And the reason for that is, remember how I said if a function is continuous, if a function goes through every single point in there, then we're talking about the points that we can't count. We're talking about infinitely many numbers in between the points we're looking at. And the best way to encapsulate, to include all of those infinitely many numbers is just saying, oh, it's all real numbers. Every possible one. Okay, so that's the first way is in words, we usually say all real numbers. And then if, let's say, we had a continuous function that was in fact continuous, so flowing, like I said, never stops, then let's say it was like this. Something that looks sort of like a y equals x function. It doesn't necessarily have to be, but let's say it the arrow that says it keeps going on and on and on and on is only on this side, is only on the right side, going up and to the right. But I said the graph actually starts at, I don't know, -1. Sure, -1. -1, -1. This point is -1, -1. But that's where it starts, and it doesn't go any further down, any further left than that. That's the absolute start of this graph, if we're looking left to right. Then I would say for the domain, it is all real numbers, and x is greater than or equal to, what do we think? Greater than or equal to -1. And the reason for that, if I look at my x-axis right here, then if I look at the very start of the graph, the smallest possible x value is -1. I can't get x equals -2. I can't get x equals -3. But I can definitely start at x equals -1. So I say in words, the domain is all real numbers starting at x equals -1. That would be one way to say it. Or we could use this inequality notation. X is greater than or equal to -1, which is the same thing as saying x, x is greater than or equal to -1, or starts at -1. I'd say this inequality way of saying this, adding this on, would be the most precise. So in words, the domain is all real numbers where x is greater than or equal to -1. So what do we think the range would be? What would the range be? First, it's continuous, right? So remember, if it's continuous, all real numbers. That's it. Because it's flowing. We have to account for every number in between. But we have to tack on something extra, because do we have this function hit y equals -2? No. We don't have it hit -3. We don't have it hit anywhere lower than, we don't have it hit anywhere lower than y is greater than or equal to -1. So that's our range. In words, y, or the range is y is all real numbers greater than or equal to -1. And that's it. Easy peasy. We have done it in words. So how could we do this in the next notation, which is inequality notation? So we've already used some of the inequality part, because we had to use an inequality to say all real numbers greater than or equal to -1. But there is a more succinct way of using inequalities only, and not even saying all real numbers. So taking this same function, remember, the function starts at -1, -1, if we're reading left to right, down to up. Then, instead of saying all real numbers, x greater than or equal to -1 for the domain, I could say the domain for this same function is x is greater than or equal to -1. We do that. But how do we get, or maybe not even there, how do we get the all real numbers part? How do we get everything that happens when we keep going and going and going and never stop? How do we get that? We say x is going all the way to positive infinity. Now notice I messed up early. I almost wrote less than or equal to. We can't do that, can we? Why? Because if I said x is less than or equal to, or less than and equal to infinity, this is saying not only is x less than infinity, but also x is equal to infinity. And we can never be equal to infinity because, honestly, I've never seen infinity. I don't know about you guys. Maybe one day, maybe not in this dimension, but I haven't seen it yet. So there's no way I could say any number is equal to it. Okay, and the same goes for the range. All real numbers, all I would have to do is say the range is y is greater than or equal to, like we said, y is greater than or equal to -1 and less than, it keeps going up and up and up and up and up, must be less than positive infinity. And that's inequality notation, because not once did I say all real numbers. All I used was inequalities and infinity. So to me, this is the next intuitive way of describing a domain and range. In words, I think is the easiest. The next would probably be inequality notation. The third is very, very much like inequality notation, but we are going to be doing interval notation. Okay, so if let's do a new function, just so we're not getting hung up on the same one and thinking that's the only way we can do things. Not that you guys are thinking that. Let's see. We had something like this for interval notation. I have an idea. How about we have a graph like this? Now, I have no idea what the algebraic or function notation for this would be. I can't say y equals yada yada, but it's a graph, and I can describe it. The first things that I'm seeing is that it keeps, if I look at these arrows, because these are the important ones. Remember what's happening all the way to the left of the graph, all the way to the right of the graph, all the way up and all the way down. That's what we want to look at, because it tells us a lot about what we can predict. For this one, it looks like it keeps going. It keeps going to the left, and it looks like it keeps going down. It looks like it keeps going to the right, and it keeps going down. That's what it looks like to me. Mostly. I don't feel confident enough to say that there's an asymptote here where it doesn't keep going right or left. It looks like it's angling that way. But I can say it doesn't look like it gets any higher than right here. Let's say it doesn't. And if I wanted to, let's call that, I don't know, y equals +2. Let's say that's our asymptote. It never gets higher than that. Maybe it hits it. Maybe it doesn't. I'm gonna say it does hit it. So let's say this graph does in fact get to y equals 2 at its maximum points. So I've looked at the graph, and let's try interval notation. First, in words, I would say, is it continuous? Is it discrete? It is continuous, so I should start my words in words with all real numbers, because it's continuous. And then, if I'm talking about domain, then let's see. If it keeps going left and it keeps going right, then it's just all real numbers. I didn't start anywhere, I didn't stop anywhere. Then in inequality form, I would say, what do we think? If it's all real numbers, has no starting or stopping place, I would have x is greater than -infinity and less than infinity. That's it. Okay. And then for interval notation, this is why I say it's not that different from inequality notation. We're just using a different set of symbols. So instead of using greater than or less than, our inequality symbols, we don't even have to put x. If we're still talking about domain, then I know it's all real numbers. I know it's from negative infinity to infinity. So one way I could write it in interval notation is parentheses negative infinity, infinity. And that's it. The cool part is if I look at the range. So let's do it on this side. If I look at the range, okay, then remember, I'm I'm gonna go ahead and say that this graph is hitting y equals 2. Does it get any higher than that? Can I get to y equals 3? I'm gonna say no. So there is a maximum here for this whole graph. Can it get lower than y equals 3? Absolutely. Can it keep going and going and going? Absolutely. This continues on and on forever. Y all the way to negative infinity. So in words, I would say, first, is it continuous? Yes, it is. So I should put all real numbers first. That's the first thing I should do. And then next, is it, or let's do inequality. Inequality for the range, remember this is range, then I would say y. I know it keeps going south. It keeps going to negative infinity. So it's greater than negative infinity. But I would say it is less than. So it starts from way down, and then makes its way all the way up to the top, and then hits y equals 2. Then I would say is less than or equal to 2. And this is our inequality range. And in interval notation, this is the neat part. This is what combines inequality and interval notation. That's that instead of having less than and then less than or equal to, like those two differences and the differences in what those symbols mean, I would have my range is parentheses, negative infinity, comma, 2, but how do I show that it's equal to? It's not parentheses, it is now square brackets. So this bracket is literally telling me that the interval goes to 2 and includes 2. It is equal to 2 as well. And then, yeah, I'd say that's a pretty good cover for interval notation. The last one, okay, this is where Algebra 2 kids, if you feel like you honestly don't care about an extra notation that you will only really use in calculus and university calculus, then move on. Get your homework done. Good job. I'm going to cover some more examples after this, so definitely skip ahead. And once you see a big title that says examples, press play again. But for honors kids, the last one and the more convoluted way of talking about notation is set notation. And sadly, like I said, set notation, as you're about to see, is really precise and very useful, but we mostly only use it in calculus and analysis because of the diction and the way we describe things is so much more accurate and precise, or needs to be more accurate and precise. So for set notation, we have, do I want to do a new graph? No, I'm pretty happy with this graph. Let's do this one as well. Then we have what would be a fun graph to look at? Let me take a look at my handy dandy notebook. If I look at an absolute value function, then can look something like that, and then something like that. Okay, then I know that in words, 1. In words, let's say we're talking about domain first. Let's say we're talking about domain first. In words, is it continuous? Is there a gap anywhere in this graph? No, it is not. So the first thing we should say is all real numbers. Next, the domain. Does it start anywhere on the left? Does it start anywhere on the right? No. It starts all the way from negative infinity on the x-axis and then all the way to positive infinity on the x-axis. So it's just all real numbers. For inequality notation, then since it's all real numbers, literally every number I could possibly get on the x-axis, then it's just negative infinity to infinity. In interval notation, then we are going to have, look at me, I'm already getting mixed up. I'm so sorry, guys. This one is interval notation. See, even Mr. A makes mistakes. That's a good lesson there. Then if that's interval notation, then inequality notation, it better have some inequality symbols in there. So we have, if we're talking about domain, we're talking about x, then greater than, not equal to, just greater than, negative infinity, less than positive infinity. Okay, now we're good. Then we have the last one, which is set notation. There's a couple of ways to do this, but the first thing you should look for in set notation, this is the telltale sign, is that we'll have our squiggly brackets. No, those are horrible. I'm so sorry. We'll have something that looks like, there we go, our squiggly brackets. I had a teacher that called them French brackets. I don't know why. Maybe because the French are fancy and squiggles are fancy. Maybe. But that's the telltale sign that we're working with set notation, is the curvy brackets. And then, since we're talking about domain, and I'm going to try to say this out loud so you guys can get an idea of what this literally means in words. Curly bracket, the set of all x values such that, and there's two ways to write this. I'm going to do the first. X is greater than negative infinity, and x is less than positive infinity. That's it. And then another set of squiggly brackets. This is set notation. So all these things here are saying the same exact thing. But I said there's one more way to say this, and you'll see this in calculus, probably BC calculus more than AB, or definitely in university calculus, which is brackets, curly brackets, the set of all x values such that x is an element of all real numbers. Okay, so this symbol here, to dissect it, because I'm sure some of you might not have seen this before. This symbol here simply means an element of. And that's a fancy way of saying it is a part of something bigger. So Mr. A is an element of the math department, or I don't know, my phone is an element of the things in my pockets. Simple enough. And then this symbol here, this line that I just drew, big strong line all the way down, simply means such that. Such that. So it's saying it is the set of all x values such that, meaning it's specifying what is it going to make all these x values true. Okay, Set notation. It is fancy and is very, very precise language. We may or may not use it quite a lot here in Algebra 2, but we're definitely going to see it again in calculus. That's all I can say about that. And it's always nice to see another way of seeing things, because if you run across it in a book, you're not going to be lost at what they're trying to say. Let's do the range, just so we get more practice. Remember, if you need to skip ahead, feel free to. If you need to rewind, rewind. If this is super easy and you're getting bored, watch this at 1.25 speed or 1.5 speed. Do what you need to. That's the beauty of recordings. So let's look at range. In words. And let's have this be a video exercise. Pause it, try it yourself. Keep going. I'm gonna do this in real time, so pause as you go. In words, I'm gonna say all real numbers because it is continuous. That's the first thing we check. And it's the range. If it's an absolute value function, so let's say this is y equals the absolute value of x, then does it ever go lower than y equals 0? No. In fact, does it hit y equals 0? Yes. So I can say all real numbers and y is greater than or equal to 0. Because everything above the x-axis, true for y. Everything below, never happens. Inequality. What do you think? Pause. Play. Y is greater than... What do we think? Greater than or equal to 0 and less than positive infinity. Because starts at 0, keeps going up and up and up. In interval, we have closed brackets, 0, because it's equal to 0, but greater than, and keeps going all the way to infinity. Infinity! And beyond. And so we have open parentheses for the infinity symbol because we can never equal infinity. Set notation. Set notation, we have curly brackets. Mine are ugly. Don't feel bad about yours. Curly brackets, the set of all y values such that. What do we think? We could do the inequality way and just copy that down. Such that y is greater than or equal to 0 and less than infinity. That's one way to write it. Could we write it as y is an element of all real numbers, full stop, nothing else? No, not this time, because if we said y was an element of all real numbers, then we're saying it goes all the way down as well, and we can't do that. You could get really complicated and say y is an element of all real numbers, and then y is greater than or equal to 0, but if you're going to put in that much effort, you might as well just write the inequality form in set notation. And that's it. Actually, yeah, we're done. We're done. What we've covered... Set notation, interval notation. Let me put a number here for y'all. Set notation, interval notation, inequality notation, in words notation. And all of these we've covered continuous functions. So sadly, we need to run through real quickly the discrete ones. And this one shouldn't take too long because you've already seen the gist of how we should do things. Okay, so discrete notations. Yeah, let's just do one graph because I think one graph can say pretty much everything we need it to say for discrete. Yeah, that sounds good. So if I have I'm not even going to call this a function. If I have this graph and I'm looking at the domain and the range of it, then let's say I have a point here at 1, 1. and also a point here at 1, 0, and then a point here at, let's see, this looks like -1, -1. I have a point here at -2, -1, -2, -3. So this one is at -2, -3. And for the heck of it, let's put one more point right there. I don't even know what that is. Let's talk about our domain. Domain first. Okay, so in words, can we call this all real numbers? Is it continuous? No, it is in fact discrete. So we can't even say all real numbers. What we do say is, in words, the domain is just the values of x that are possible. So for here, I said -2, so this is -2, -1, and then 0, 1, 2, 3. Okay, so that means here we have a x value of -2. Here we have an x value of -1. Here we have an x value of 1, and also here we have an x value of 1, and here we have an x value of 3. So I'm literally just going to say the domain is -2, -1, 1, and 3. That's it. Do we have to say 1 twice? Because there is a point here and a point here. If you ask that question yourself, great question. And the answer is no, because there is no point in writing the x value 1 more than once. We just know that at that x value, this domain is true. So next, in inequality form, right? Well, let's think about that. Can we write an inequality for an x value? Could I say x is greater than or equal to -2? No, not really, because if x was equal, or if x is greater than or equal to -2, yes, it's equal to -2. Perfect. We already caught that here. But is it greater than -2? Because if x is greater than -2, we're also saying that it's true here, 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 and here, and here, and here, and here, and here, and here. Which we can't say, because there's space here. There is no point there. So we can't say that. So, rather than adding any inequalities at all, we just say it's the same thing as in words. This is the inequality notation of the domain. It's the same. For interval notation, let's think. Let's think very carefully about this. If I wanted to show an interval, right? That means there is a length to this interval. Sometimes that interval could be -infinity to infinity. A very, very big interval. But what if I had the interval of a single number? Is that possible? Does a single number even have length to take up as an interval? Well, luckily intervals don't have to have length. They can just be a single number. So this interval of close bracket is equal to -2, close bracket gets to no further than -2, is in fact an interval. So x equals -2. This notation here, close bracket -2, close bracket -2, is the same thing as saying x equals -2. So what do I do for the rest of the points? I just keep going. I say comma, close bracket -1, comma, close bracket 1, comma, last one, close bracket 3. And again, do I need to add more than one close bracket for these 2 points? Nope, not at all, because it includes both. Now, set notation is, maybe it's easier, maybe it's not. You saw how it was for continuous functions. Set notation for the domain here is going to be, now say it out loud with me if you can, because it helps. Squiggly bracket, the set of all x values such that. Now, what do we write? All we have to write is what we wrote up here in words and inequality. We don't even have to use the interval closed brackets because it's assumed. So all I have to say is the set of all x values such that x is -2, x is -1, x is 1, and x is 3. That's it. Next step, jumping into range. Okay. In words, I'm going to leave this for y'all to decide. Pause the video, take a look at the notes that I'm definitely going to upload on this, and try to do this for yourself. See if you can get far on the range. I think the only thing I will say, because it's not that different from the domain, is that when we're talking about, remember when I asked on this section right here, do I need to write x equals 1 more than once? No. Once is just fine. But for the y values, since there's 2 points directly on top of each other, then that means at this point y equals 0, and at this point y equals 1. These are two completely different y values we need to worry about, so you have to account for both of them. That's all I'm going to say about that. If you have any questions on this, feel free to email me. That is discrete notations. We've covered set notation, interval notation, inequality notation in words. We've looked at some continuous graphs, some discrete graphs, and we saw how it's a little different if we're talking about discrete graphs. That's it. Good job. This is a lot, and I agree. Take a look at the homework. If you have any questions on it at all, or if you try one and you're not sure if you're on the right track, just take a picture, email me. That's all you gotta do. That's all for today. Mr. A signing out. Go do some math.